thank you all for being here and listening to me. So I come from the University of British Columbia, and this is a picture of our campus. It's in Vancouver, in Canada, up in Canada. And yeah, it looks very pretty. And do I have a laser pointer or something?
Yes, you do.
And where is it?
Well, that's the trick, isn't it?
I have a pen and a...
That's it.
That's it?
You have it here. Didn't work. I might, wait.
I have one, I think.
Yeah, one. Doesn't matter. I can jump up. Fine.
I just put a guy racing there.
All right, doesn't matter. So let's just get going and.
Oh, here it is.
Perfect. All right.
I
So
got
what I'm going to talk today about, what I'm going to talk to you about is cold molecules. And I work in the chemistry department, so there's going to be a lot of chemistry in my talk. Not the typical kind of chemistry that chemists would normally talk about. See, I'm in a kind of an unusual situation because most chemists will think of me as a physicist, and most physicists will think of me as a chemist. So I don't actually know what I am, but I am going to be talking about some chemistry today. But if you want a general introduction to the research field of cold molecules, I would recommend two references to you, because both of them will have my name on it. And so this is one of them, the book. You probably don't want to buy it, but you could get it in the library and browse through it. There's also this paper that Junia and a couple other people and I wrote a couple of years. Is it 2000? No, this is supposed to be 2009 actually, a couple of years ago. And so this is also a very lengthy but a comprehensive introduction to the field of cold molecules. So this one is available for free, to download for free, and I recommend that you download it and correct this. All right, very rigorous. All right. So this is what I'm going to try and discuss today. So I'm going to talk to you about the microscopic. Today I'm going to talk to you about the microscopic two-body interactions that determine the dynamics of ultra-cold atoms and molecules. And I'm going to be talking, a lot of my talk today will be about problems. Of course, in physics, we don't use the word problems, we say challenges. I'm going to be talking about challenges that we have to meet and overcome in this field. So I'm going to be talking. I'm going to start by telling a little bit about external field traps for atoms and molecules, and the interactions of complex atoms. I'm going to try and go. We've already heard about alkaline metal atoms and also alkaline earth atoms. But I'm also going to try and go beyond that and try and discuss the prospects for cooling and other than alkaline metal atoms. Because there's a lot of interesting physics one can potentially do, physics and chemistry, one can potentially do with atoms that are non-alkaline metal atoms. Then I'm going to go on and tell you a little bit about interactions of ultra-cold molecules, and the rest of my talk will then be about ultra-cold chemistry. I'm going to tell you where we are in this field. I'm going to discuss the challenges, and I'm going to give you my personal perspective on where this field is going to go in the next couple of years or so. All right. Well, I just wanted to start off by showing you this slide that kind of summarizes, kind of underlines, why there's so much interest in ultra-cold systems. Now, if I counted correctly, there were as many as 12 Nobel Prizes awarded to 27 scientists for research in low-temperature phenomena since 1913. Okay, so if you work in the field of ultra-cold gases, of course, these two you have to know about. And the 1997 prize that was given for the development of methods to cool and trap atoms with laser light, and the 2001 prize that was awarded for the achievement of the of the Bose-Einstein condensation. And now that Troy Glauber entered the room, I realized that I should have also mentioned the 2005 prize, but I'm sure Troy will forgive me for not mentioning it. Right? But what I wanted to say is that there's one more prize that no one knows about yet, because it hasn't been awarded yet, and that is for ultra-cold chemistry. And the name attached to this can be any one of yours. So and I'm going to try and argue why this is so interesting, and hopefully get you excited about it. Well, another thing I wanted to mention before I start is, I wanted to show you my temperature scale. Okay, so I'm going to be talking about cold and ultra-cold atoms and molecules, and so we're going to be in this temperature regime. Cold is anything below a Kelvin, and ultra-cold is anything below a millikelvin. Okay, there's also warm and hot, but I'm not interested in this kind of insanely high temperatures. Right. What I wanted to mention is that
it's only in Canada that anything above 10 Kelvin is considered hot.
Well, I'm from Canada. Right? So, that's a good point. So in Arizona, you have to go down that way. So, I wanted to mention that there are many experimental techniques that have been developed over the past 10 years that can easily get you down to a temperature of about 1/10 of Kelvin. Okay, there's a variety of different techniques for cooling atoms, different kinds of atoms, not just alkaline metal atoms, and also molecules. Okay, and I'm going to list just a few of them, but this list is by no means inclusive. So there's buffer gas cooling, there's laser cooling. Laser cooling for molecules, incidentally, was demonstrated just recently by the group of Dave DeMille. So until like 2 years ago, everybody would say that laser cooling molecules is impossible. We should not say this anymore, because there have been experiments published and demonstrating that laser cooling of molecules is possible. There's steric deceleration, there's velocity filtering, there's several other different techniques that you can read about in the paper that I mentioned on my slide 2. So these techniques can easily bring you down to the temperature of about a 1/10 of a Kelvin. Okay, but the interesting physics that we're going to be talking about today, and that many of these previous lectures were talking about, happens down here, or a temperature even below this temperature. So if you want to be here, you can easily get here, relatively easy. It's relatively easy to get here. You want to be here. And currently there's a major thrust of research. It's a major problem in this field, how to bridge this gap. So there are a lot of experimental work. There's a lot of experimental work focusing on bridging this gap. So far, kind of unsuccessful. Okay. So it's actually not just about temperature that we have to talk about when we talk about this field. It's actually the density that also matters. So what you want to be is not just ultra cold. You want to be you also want to have a very dense ensemble of atoms and molecules. Okay, so actually some of the experimental techniques that I mentioned here, for example, the steric deceleration, can generate molecules at very cold temperatures, except that they would do that at the expense of the density of molecules. So you could actually bring molecules from here down to the ultra-cold regime, but by doing this, you're going to be losing a lot of molecules. So what you end up with is a sample of ultra-cold molecules with a very low density. Okay, so and this is demonstrated by this graph here that shows that basically it shows that we have to care about both the temperature and the density. Okay, and what we want is to move in this graph. We want to move up this way. Okay, because if you look on the right side of this slide, this is this graph here lists potential interesting applications of ultra-cold atoms and molecules, and there's many interesting things you can do with atoms and molecules that have ultra cold temperature and very high density, that have very high phase space density. So what you really want is to go up here, okay, and this remains to be a challenge. Okay. So what we want is to be ultra cold and dense. All right, the other thing I wanted to mention is that if you look in interstellar space, the coldest temperature, come in. They're not very interested. I thought this slide was very exciting. And it is exciting because really what it shows is that the coldest temperature in the universe is in the warm regime, in the Canadian warm regime. Right? Actually, the coldest temperature in the interstellar space is about 2.7 Kelvin due to the background radiation and other reasons. So it's 2.7 Kelvin, right? What we're interested in is temperatures much lower than the coldest and the lowest temperature in the interstellar space, in the universe. So if you want to get to these low temperatures, therefore, the first thing you need to do is isolate your sample of atoms and molecules from the rest of the universe. And how do you do that? Well, you do that by confining atoms and molecules in external field traps. And the simplest possible kind of trap, and the kind of traps that have been used for alkali metal atoms in the experiments leading to the Bose-Einstein condensation, are magnetic traps. Conceptually, this is a very simple idea. So what you have two coils, and you run current in these coils in the opposite direction. This is called the anti-Helmholtz configuration. And if you do this, you're going to generate a magnetic field potential in the space between the coils that will look like this. So there's going to be the minimum of the potential in the center of the trap, and the magnetic field is going to increase when you go away from the center. Okay. Now, if you have atoms or molecules that are paramagnetic, that have non-zero electron spin, okay, they will interact with the magnetic field, and in some states, the atoms or molecules, they will have their potential energy. The potential energy is going to increase as they go away from the center of the trap. So therefore, they're going to be confined and trapped. So if you have them trapped, you can then do what they do in the experiments with alkali metal atoms. You can evaporatively cool them. Okay? And the idea of the evaporative cooling, I'm just going to go over this very quickly because you probably have heard about it before. The idea of evaporative cooling is also very simple. So what you do, you start with a sample of atoms or molecules in a trap like this, and then so you're going to have a Maxwell-Boltzmann distribution of these atoms or molecules in the trap. The hottest particles are going to be living near the edges of the trap. So if you just decrease the trap depth, or if you apply a resonant RF field that will drive your molecules or atoms from the trappable state to an untrappable state, and it would be resonant, with the molecules or atoms that are sitting near the edges of the trap. Okay, so by doing this, you're going to be expunging. You're going to be getting rid of the hottest particles in the trap. And if you get rid of the hottest particles in the trap, and you let the rest of them collide and re-equilibrate their kinetic energy, you're going to lower their temperature. Okay. So there's another way to look at it, in terms of Maxwell-Boltzmann distribution. So if you start with the Maxwell-Boltzmann distribution depicted by the red curve here, and get rid of the hottest particles, what you're doing really, you're chopping off the highest energy tail of the Maxwell-Boltzmann distribution, right? And then if you let the particles collide and re-equilibrate their kinetic energy, you're going to generate another Maxwell-Boltzmann distribution, and that one will be described with a blue curve here. So it will correspond to a lower temperature. Okay? And that's what they did really, to get to the Bose-Einstein condensate in the Gila experiment and in many other experiments, in the MIT experiment of Open Ketterle, and many other experiments throughout this country. Okay. So this is really what happens, when a cup of coffee is getting cool, right? The hottest molecules escape the beverage, and then the rest of them re-equilibrate their energy. Okay. Now there's good news about this, and there's bad news. The good news is that it works for alkali metal atoms. You know that. But the bad news is that collisions can be, well, there are two types of collisions. There are good collisions, there are bad collisions. And you need collisions in order to re-equilibrate the kinetic energy in the evaporative cooling experiment, right? So the good collisions are the collisions that preserve the orientation of the electron spin of the atoms and molecules. They have two particles whose spin is oriented along the magnetic field axis or anti-parallel to the magnetic field axis. They collide, and if their spin orientation remains unperturbed, this is a good collision because that's the collision that keeps the atoms or molecules in the trap, but at the same time it's the collision that leads to exchange of momentum between the atoms and molecules, and it leads to the re-equilibration of the kinetic energy. However, the atoms and molecules, when they collide, when two particles like this collide, they can also change their spin orientation. So two particles with the spin up can come together, and then as a result of the interaction process, both of the particles can flip the orientation of their spin. Okay? And when this happens, the particles actually undergo a transition from the state whose potential energy is depicted by the blue curve here, or the blue line, to the state with the potential energy depicted by the red curve here. So what this is the potential energy of the atoms and molecules in a magnetic trap as we go away from the center of the trap. So this state here is trappable because if the potential energy of atoms and molecules in this state increases as we go away from the center. This state is untrappable, okay, because the potential energy of the atoms and molecules decreases as we go away from the center. Okay. Now, is this too simple? Should I speed up? Yeah, the other thing I wanted to mention is that you definitely need to speak up, and if you have any questions, because I really want this to be more of a dialogue than a monologue. So if you have any questions, anything, because really, if you have a question, the person sitting next to you will most likely have the same questions, just that he or she is too shy to ask it. So you're going to do a favor to the person sitting next to you if you ask the question that's on your mind, because I want to be interactive. All right. So now the question is, why does this work for alkali atoms? So we know that it works for alkali atoms, alkali metal atoms. We know that alkali metal atoms are unlikely to undergo the transition from the blue state to the red state when they collide. And the question is why? So can you tell me why? Now you're waking up. So why do you think the process of changing the spin orientation in collisions of alkali metal atoms is not very probable? Well, I'm going to come back to this question. I'm not going to answer it now, but I'm going to come back to this question, okay, after I answer these questions. So what about other kinds of atoms? Like the periodic table has many more atoms, not just alkali metal atoms. What about molecules? Okay. So this is the periodic table. And this periodic table summarizes the state of the art in the field of ultra-cold atom physics for year 2004. Okay. So what this shows, that the atoms sitting in this pink squares are the atoms that have been magnetically trapped. The atoms that have this yellow box, they are actually atoms that were cooled to quantum degeneracy. So, but if you look at it, and just a glance at this table shows you that only a handful of atoms have been, were magnetically trapped in year 2004. The alkali metal atoms, chromium, magnesium, molybdenum, and this strange thing here. Okay? So, in year 2012, there were a few more atoms that were magnetically trapped. Scandium, titanium, copper, and silver. Fortunately, they couldn't get gold. I suggested them to trap gold because it would be a golden trap or a gold trap. So nitrogen and this species here. Okay, still the majority of atoms. It's hard to trap the majority of atoms. So now, what makes magnetic trapping of most atoms difficult? Or what makes evaporative cooling of atoms? These atoms, they were magnetically trapped, but they were not evaporatively cooled. So what makes evaporative cooling of atoms in a magnetic trap difficult? Okay. Well, let's take a look at a typical atom of interest in chemistry, like oxygen atom. Okay. The ground state of oxygen is triplet Pj. The ground state is actually J equals 2. So it has the electronic orbital angular momentum and the spin angular momentum both equal to 1. Right? Now if I look at the interaction of this atom with the magnetic field, it's going to be described by this interaction term. Okay? This is the Zeeman interaction, this is the electron spin and the electron orbital angular momentum. Okay? And the Zeeman energy levels of the oxygen atom, they look like this. Okay, so this is the trappable state. Well, this state is also trappable. These two states are untrappable. Okay, so imagine now if I were to trap oxygen atoms magnetically, say in this state. Okay. So what would happen if I were to collide these oxygen atoms in a magnetic trap with other kinds of atoms? And for simplicity, I'm going to describe in the following collisions of oxygen atoms with the simplest kind of atoms, helium atoms. Helium atoms are nice because they're spherically symmetric, they're very small, so they're very nice for probing the interatomic interactions. Okay? So the problem with oxygen atoms is that, the ground state of oxygen is L equals 1. What L equals 1 means is that the electronic wave function describing the ground state of the atom has a non-spherical shape. Okay? Now, if this thing collides with helium, and this red ball here represents a helium atom. Okay? Now, depending on the approach angle, so the helium atom can come and interact with the oxygen atom this way, or it can come in this way. Depending on the approach angle, the interaction is going to be different. Okay? So the interaction between the helium atom and the oxygen atom is going to be anisotropic, it's going to be angle dependent. Okay. So how do we describe this electronic interaction of anisotropy? Because you know that in quantum chemistry what we do when we have two atoms, we calculate the interaction potentials. The interaction potentials between atoms, they're just one-dimensional curves. Right? But if I just forget about quantum chemistry for a moment, okay, and if I look at this picture here, what I see is a potential that's a function of the distance, this distance here. It's a function of some other vector, little r, that can orient arbitrarily in space. So if I have a function of two vectors and an angle, I can generally expand it in Legendre polynomials, for example, right? In any angular basis that's complete. Okay, so I can represent this function as a function that is an expansion like this, where the expansion coefficients depend on the distances and not the angle. Okay. Now the term with lambda equals 0 in this expansion is going to describe the isotropic part, or the spherically symmetric part of the interatomic interaction potential. And this term will determine the elastic interactions between the atoms. That is, the interactions that do not change the internal state of the atoms. So when the atoms collide and do not change their internal state, that's elastic collisions. Okay? The states with lambda greater than 0, the terms with lambda greater than 0, they will describe the anisotropic part of the interaction potential. And it's this anisotropy, it's the terms with lambda greater than 0 that will lead to inelastic scattering between the atoms. It's this interaction part, it's this part of the interaction potential that will lead to trap loss. Okay? So can we actually calculate this anisotropy? And as I mentioned to you already, in quantum chemistry, when we think about interatomic interactions, we typically think in terms of interaction potentials like this. Okay? So this would be the interaction potential between two, say, alkali metal atoms. Okay, now if we have an atom with a non-zero orbital angular momentum L, when L is not equal to 0, it happens, the interaction between the atom with non-zero L and another atom will always give rise to multiple interaction potentials. And it's easy to understand why, because the different electronic states of molecules are determined by the projection of L on the interatomic axis, right? So if you have an atom like oxygen atom, which has L equals 1, and you have a helium atom, the helium atom has L equals 0, and you look at the interaction between helium and oxygen, okay? The L equals 1 can have two different projections, L equals 0 and we denote it usually by lambda. It can have two different projections, lambda equals 0 and lambda equals 1, okay? So therefore, if you bring an oxygen atom and a helium atom together, you're going to have two different interaction potentials that correlate with the limit of separated atoms. Okay? So these two interaction potentials, we in chemistry we call them sigma and pi interaction potentials. Sigma and pi. And it turns out that through some angular momentum algebra, we can relate this sigma and pi interaction potentials. So these are the interaction potentials that I would calculate by solving the Schrödinger equation for the two-atom system. Okay? And then through some angular momentum algebra, I can relate this interaction potential to the terms in the angular expansion that I showed you on the previous slide. Okay? So I can show that the lambda equals 0 term is always going to be some sort of a linear combination of the different potentials. In this particular case, it's b sigma plus 2b pi divided by 3. And I can show that all of the lambda greater than 0 terms will be related to the differences between the interaction potentials. So this difference here, so what I'm plotting here is the difference between these two potentials. So this will determine the anisotropy. This will determine the inelastic scattering of atoms with non-zero orbital angular momentum. And as you can see here, for this case of oxygen interacting with helium, this interaction is pretty strong. It's on, well, what I'm plotting here is energies in the units of wave numbers, and you can think of wave numbers as Kelvin. One wave number is approximately equal to 1 Kelvin. For the purpose of my talk, let's think of the two as the same. It's 0.695 wave numbers equal to 1 Kelvin, or the other way around. I don't remember exactly. But in any case, so I usually think of wave numbers as Kelvin. So you can think of this anisotropy as about, as something like 10 Kelvin here, right? And that's much greater than, of course, the collision energy of atoms, in a magnetic trap. Okay. Now, if you have an atom with a higher orbital angular momentum than L equals 1, then you're going to have more interaction potentials. For example, for the case of oxygen in the first electronically excited state, which is a D state, singlet D, interacting with helium, you have three different electronic interaction potentials in the molecule. They're of sigma, pi, and delta symmetry. And the electronic interaction in this case will likewise be described by the electronic interaction and isotropy in this case will likewise be described by the splitting of these potentials. Okay? So now how does this affect the probabilities for the trap loss, the probabilities for the inelastic collisions that I talked to you about? Well, this is the calculation that shows, the probabilities of the bad collisions. That's the red curve here. Well, I'm plotting here the cross section, but you can think of this as the probability of the Zeeman relaxation that leads to trap loss. That's represented by the red curve. And the blue curve shows the probability of elastic scattering that determines the energy re-equilibration in the trap. Okay, and as you can see, at temperatures below 10 to the negative 2 Kelvin, at collision energies below 10 to the negative 2 Kelvin, the probability of the bad collisions is greater than the probability of the good collisions. Okay? So it's going to be very hard to keep these oxygen atoms in the trap. And this is for collisions with helium. And like I told you, helium is a very small isotropic compact atom. So if you replace helium with anything other than helium, the bad collisions will become much, much more probable. Okay? So what this indicates is that it's going to be very hard to evaporatively cool oxygen atoms in a magnetic trap. Have a question?
Yeah, sorry. How did you calculate the probability?
So I'm just saying that, what I'm plotting here is the cross-section, because the cross-section is what I calculate by solving the Schrödinger equation. But what the cross-section represents is really the probability of elastic and inelastic scattering. You can think of it as the probability. Okay? Because the cross-section is directly related to rate. And so basically, you could also think of this as representing the rate of inelastic scattering and this representing the rate of elastic scattering. Okay? All right, now I showed you this, and I told you that these atoms have been trapped in a magnetic trap. Okay? Now, many of these atoms are also atoms in non-zero orbital angular momentum. Oh, incidentally, I should address that question that I posed. Well, why are the alkaline metal atoms? Why can we actually cool the alkaline metal atoms? let's go back to this picture here. For alkali metal atoms, L is equal to 0, right? The alkali metal atoms are in the S state, okay? And that's why there is no torque due to the angular dependence of the interatomic interaction potential that would drive the inelastic collisions. So if you expand the interaction potential between the two alkali metal atoms in this form, there will only be one term in the expansion. In this expansion, there will only be one term with lambda equals 0. So the electronic interaction potential between two alkali metal atoms is, to first order, it's isotropic. Okay? And that's why alkali metal atoms, when they collide in the magnetic trap, they don't usually undergo the Zeeman relaxation. They don't usually change the orientation of their magnetic moment. For most atoms in the non-zero, in a state with a non-zero electronic orbital angular momentum, this will not be the case. Okay? Except that I showed you this periodic table, and I told you that these other atoms have been trapped over the past 6 years. There's a lot of work in an effort to cool and trap these kind of strange atoms. Many of them are in states of non-zero electronic orbital angular momentum. So how come we can trap these ones in a magnetic trap? Now I should tell you that these atoms here, these atoms, they were trapped in a magnetic trap in the environment of a helium buffer gas. Okay? So they were cooled to sub-Kelvin temperatures by collisions with cold helium atoms. Okay? And then they were magnetically confined in a magnetic trap. Okay? So collisions with helium did not apparently lead to trap loss. And why is that? Well, if you look at the electronic configuration of these, these are lanthanides, right? Of the lanthanide atoms, like scandium or titanium, you will notice that the electrons that populate the electronic orbitals with non-zero angular momentum, they're kind of buried, they're submerged under the S-state electrons, the electrons living in this 4s orbital here. And the 4s electrons are, of course, spherically symmetric. So in these kind of atoms, the electrons carrying the non-zero electron orbital angular momentum are kind of shielded by the electrons that have zero angular momentum. Okay, let's see what it does to the electronic interaction potential. So here I've got the same picture that I showed you already for the interaction between oxygen in the singlet D state and helium. And as you can see, the splitting at the bottom of this potential wells is on the order of 30 Kelvin or so. If you look at the same, so now if you replace oxygen with scandium, scandium is a much heavier atom. It should be much more diffuse. It's much, it's very far below oxygen in the periodic table. But if you look at the same interaction potentials between scandium in a doublet D state and helium, you're going to see this. And that's the effect of this shielding electrons. So you see, the different electronic potentials can now become nearly degenerate. The splitting between them becomes on the order of a fraction of a Kelvin. Okay? Now, if you look at the probabilities for the elastic and inelastic scattering, in the case of oxygen with helium, I already showed you this. Okay, for scandium helium, it looks like this. See, this is now the probability of good collisions, and this is the probability of bad collisions. And as you can see, for a wide range of energies, the probability of good collisions for scandium is much greater than that for bad collisions. And that's why, in the experiments of John Dole at Harvard, they could actually trap scandium atoms in the environment of helium. And they could keep the atoms in a magnetic trap for a long enough time to do the measurements. Okay. Now, even though this is encouraging, you can do this in the environment of a helium buffer gas. You know, if you replace helium with another scandium atom, the situation becomes significantly worse, because now you've got, two heavy polarizable atoms in states of non-zero electronic orbital angular momentum interacting, and the electronic interaction in the substrate is just going to be too big for you to be able to keep the atoms in a magnetic trap. So unfortunately, even though you can trap these atoms in a magnetic trap in the environment of a helium buffer gas, unfortunately it's impossible to evaporatively cool them. So if you get rid of helium and then just try to collide scandium with scandium, the electronic interaction in the substrate is just going to be too big. And so it will bring this curve way down here. Okay. Now what about molecules? Okay. Well, formally, you can think of interactions between molecules in the same way as the interactions between atoms. Now, this may look surprising to you, but if you look at this picture, you'll see what I mean. Okay? So, you can think of this as an atom in a p state, just like the oxygen atom I discussed a couple minutes ago. You can also think of this as a diatomic molecule. So if you have two diatomic molecules, okay, they will be described well, the interaction of two diatomic molecules will be described by these three vectors. The vector I call RA, the vector I call RB, and the vector I call R. RA describes the orientation of this molecule, the first molecule, in a three-dimensional space. RB does the same for the second molecule. And R is the vector that describes the orientation of the center of mass separation in the three-dimensional coordinate space. So if I have an interaction potential, the interaction potential that describes the interaction of these molecules is now going to be a function of these three vectors. And if I have a function of three vectors, I can expand it in a series like this, where I have the expansion coefficients that depend on the magnitude of these vectors only, and then I have the angular part that depends on the orientations of vector RA, vector RB, and vector R, big R. Okay. We can compare it to the similar expansion for atoms. So this is the one for two open shell atoms. It's a little more complicated than the one I showed you before, because the one I showed you before was for the interaction between helium, and helium is a spherical symmetric atom, and an atom with a non-zero orbital momentum. Now, this is a general form that describes the interaction of two open shell atoms, like two scandium atoms. And if you compare this to the interaction potential that describes two molecules, there's an apparent analogy here. Now, these operators here are not spherical harmonics in this case. They're somewhat more complicated, spherical tensors that have somewhat different properties, but they're not very different actually. So if you're interested in this, you could read this paper. Okay, so the only point I wanted to make here is that formally, you can think of the interaction between two molecules in the same way as you think of the interaction between two open shell atoms. Okay? So the interaction potential between two molecules is very anisotropic. It's typically very anisotropic. And you can see this from this graph here that shows a fully quantum calculation of the elastic scattering and the probability for these inelastic collisions that are determined by the angular dependence of the interaction potentials in collisions of two oxygen molecules in a magnetic field. And I'm showing this as a function of the magnetic field at a temperature of half a Kelvin. And you see, in order to bring these two curves, the dashed curve here represents the probability of this inelastic relaxation that leads to track loss. And the solid line shows the probability of elastic scattering. And you see, in order to bring these two curves down and to plot them on the same graph, I had to divide the probability of inelastic relaxation by a factor of 10. So what this indicates is that the interaction potential between two molecules is going to be very, like as the molecules come together, come close together, the interaction between the two molecules is going to be very anisotropic. It will depend on the angles very, very much. Okay? And this angular dependence on the potential is going to drive the molecules out of the trap. Okay? Okay, so it's going to be very hard. No one has actually done the experiments yet, but it's going to be very hard to evaporatively cool molecules in a magnetic trap. So how to get around this problem? So why not to trap atoms or molecules in the high field sigma state, like in the state shown here by the red line? So why not to trap oxygen atoms in the lowest energy Zeeman state, and then we don't have to worry about the relaxation, right? Because then the atoms are in their absolute ground state. When they collide, they have, nowhere to relax to. They have nowhere to go. Okay. Now the problem is, so if you were to trap the oxygen atoms in this state, they would be stable even in a magnetic trap. The problem is, in order to trap atoms in this state, in the high field sigma state, this is called the high field sigma state. In order to trap the atoms in the high field sigma state, you need to generate the magnetic fields, magnetic field potential that would look not like this, but that would have a maximum at the center of the trap, and that would decrease as you go away from the center of the trap. Now, in 1842, this guy, Samuel Earnshaw, proved a theorem that basically says that a collection of point charges cannot be maintained in a stable stationary configuration. Well, I pulled it up from Wikipedia, but that's what it says, right? A collection of point charges cannot be maintained in a stable stationary configuration solely about the electrostatic interactions of the charges. Okay? Well, then, because when you read this, you start wondering, what about atoms? And but the answer to that is that's why I need quantum mechanics and all the rest. It's the Pauli exclusion principle actually that keeps atoms stable. All right? But the bottom line of this is that it's impossible to create a static magnetic field with a local maximum. Okay? So you can generate a magnetic field potential that would look like this, but you cannot generate a static magnetic field potential that would look like this. Okay? Now the same applies to electrostatic potential. So you can generate an electrostatic potential that will have a minimum in free space, but you cannot generate one that would have a maximum. Okay? So you cannot trap atoms in a high field seeking state in a magnetic trap. So what about an electrostatic trap? Okay. Well, to answer this question, we have to look at the static energy shifts of molecules. Molecules, when you expose them to an electrostatic field, they show energy shifts that are called charge shifts. Okay. And for a simplest diatomic molecule, a molecule in a singlet sigma state, the charge shifts, they look like this. Okay? So these are the rotational energy levels of a molecule as a function of the electric field. And as you can see, the ground state goes down with the electric field. And it's actually generic. Any ground state will always decrease in energy when you apply an external electric field. Okay? So what that means, you cannot trap this state in an electrostatic trap because of the Earnshaw theorem. Okay? So you can only trap this state, so the state whose potential energy would increase as you increase the electric field. Okay? And the transition from this state to this state in collisions of molecules would also be determined by the interaction and isotropy, between the molecules. And that is, as we already saw, is very, very strong. So electrostatic traps suffer from the same problem. Okay? Then, of course, we can do optical traps, and Professor Yeh already told you about optical traps. I don't have to say much about it here. An optical trap is real, but it is really just a focused laser beam. Okay? So if we focus the laser beam like this, and you look at the transverse intensity profile, we're going to see that the intensity of the electromagnetic field is the largest at the center of the trap here, and it decays as you go away from the center. So these can be used to trap high field seeking states. So you can use this to trap atoms and molecules in the lowest energy high field seeking states. Okay. Now I wanted to mention here that you could, normally people use optical fields for optical traps. But when it comes to molecules, you could potentially also use microwave traps. So if you have a microwave trap in focal microwave cavity, you will have the microwave field intensity, the largest at the center of the trap, so that the profile is going to look like this. So the molecules whose potential energy decreases with the strength of the microwave field would be most likely confined to the center of the microwave cavity. So this idea was proposed by Dave DeMille and his collaborators back in 2004. No one has realized, no one has actually experimentally built a microwave trap yet, and I'm going to tell you in a second why it's actually going to be challenging to do this. But before I go into that discussion, I wanted to show you the energy levels of a molecule in a microwave cavity. Well, let's first take a look at how you would normally calculate them. The easiest way to calculate the effect of a microwave, of a strong microwave field in a cavity on the rotational structure of a molecule is using this formalism, where you take the molecular Hamiltonian, which is just the rigid rotor Hamiltonian, and then you take the Hamiltonian that describes the microwave field, where these are the photon creation and annihilation operators, and this is the mean number of photons in the cavity. And then the molecular field interaction is going to be described by this term here. Okay? So if you then expand your wave function in this basis set, the basis set that describes the rotational states of the molecule and the photon states of the field, Well, the metric solution is going to be like this, and then you can diagonalize this matrix to get this. So you're going to see that, for example, let's just ignore this back panel here because it's kind of complicated. But let's look at this one. So if you have light of circular polarization, then the lowest energy state is going to do this. It's going to be separated from the other energy states, and it's going to go down like this. So in principle, you could trap molecules in this state. So in principle, you would think that this is the absolute ground state of the molecule. You could trap molecules in the microwave cavity, except that if you go back to this slide, except that if you change this n bar by 1, okay, you're going to generate another structure, another series of energy levels. That, if you decrease this by 1, you're going to generate another series of energy levels that will be down here. So this energy level pattern actually repeats itself, for a different number of photons in the microwave cavity. So in the microwave cavity, this is not the absolute ground state. Okay, there's going to be another state just like this that would correspond to the mean number of photons in the cavity equal to n bar minus 1. And then there's going to be another one corresponding to the mean number of photons in the cavity equal to n bar minus 2, etc. Okay? So what this means is that molecules, when they collide in a microwave cavity, they can undergo a process that I call the collision-induced absorption of microwave photons. They can, when they come together, and even if the microwave field is off resonant, when the molecules come together, their interaction potential can actually bring the rotational energy splittings in the molecules in resonance with the microwave field. And then the microwave photon is going to be absorbed, as a result of which the molecules are going to be promoted to the rotationally excited state. And then this energy of the rotational excitation is going to be released into the kinetic energy of the molecules. So you're going to be heating molecules by this collision-induced absorption of microwave photons. And we did a lot of calculations to actually show that this process is going to be very, very efficient in the case of molecules, simply because the intermolecular interactions are very strong and they're very anisotropic. So it's going to be very hard to cool molecules in a microwave cavity by evaporative cooling. Okay? So this leaves pretty much the only method for the creation of ultra-cold molecules. And Professor Villa already mentioned this. This is the way they generate ultra-cold molecules. They do this by bringing together pairs of ultra-cold alkali metal atoms. Okay? And this is known as the photoassociation. So basically, you have a pair of two ultra-cold atoms, and then you can bring them together by two laser, photons to potentially generate molecules in the absolute ground state, like shown on this graph here. I'm not going to go into details about this because it's already been discussed, and it's becoming kind of a standard technique. This has been done by many people, except that Junier and his collaborators were probably the first to generate a very dense sample of ultra-cold polar molecules in the absolute ground state down here using photoassociation. It took almost 10 years to develop this technique to the point that it can actually produce molecules in the absolute ground state. Okay, so let me summarize what we've learned so far. Okay, so I told you that the evaporative cooling of alkali metal atoms in a magnetic trap, we all know that. It has been successfully demonstrated. And it has been used for the creation of the Bose-Einstein condensates. Okay, but so far, it has been limited largely to the alkali metal atoms. Okay. Now, the evaporative cooling of non-acetate atoms, the majority of atoms in the periodic table are non-acetate atoms. Unfortunately, the evaporative cooling of non-acetate atoms in a magnetic trap is unlikely to work. The experimental work of John Dahl and a lot of the theoretical calculations that we did and other people did shows that it's probably not going to work. Okay? The evaporative cooling of most molecules in a magnetic trap will also going to be very hard. Simply because the interactions between molecules are very, very anisotropic. They are very angle dependent. So we need to develop traps for atoms of molecules in the absolute ground state. You can do that with optical traps, but optical traps, they have their own problems, and so you can do this with optical traps, and that's what a lot of people are doing now. But we need other kinds of traps as well. Okay. And finally, so far, the best method to create ultra-cold molecules is photoassociation of ultra-cold atoms. Okay, now it would be a good time to take a break if you want one, or I could just keep going. What do you prefer? 5-minute break? Well, how about we take a 5-minute break and think about this, and I can answer any of your questions, if you have any, and then we'll continue in 5 minutes, right?
Okay.
Good.
Should I smile?
Yes.